Okay, so let me continue the discussion about the topology, and then I'll move on to a little bit about quantum geometry. Yeah. So, earlier this morning I described the train insulating state and the quantum Hall state in the Dirac system, and now let me move on to the time reversal invariant topological insulator, also known as quantum spin Hall insulator in 2 dimensions. And this started from the work of Kane and Mali. Using the model of graphene, they introduced a new term, which involves the spin-orbit coupling. And it can be viewed as a sort of a spin-full version of the Haldane model. So essentially, spin-up electron sees this Haldane flux. Spin-down electron sees the opposite Haldane flux. Now, the origin of this term, spin-orbit coupling term, that one can think of the following way. So the spin-orbit coupling microscopically for an electron moving in the presence of an electric field, let's say coming from the ions, the ion potentials, is of this form. It's P cross E dot S. So that's why we think of spin-orbit coupling as a relativistic effect that an electric field acting on moving electron generates a Zeeman field that couples to the spin. Right? But the same term can also be written in this way, right? E cross S dot P. So this means that an electric field, it actually creates a spin-dependent flux, right? In other words, there's a vector potential which is opposite for the 2 spin states due to the electric field. And vector potential couples linearly to the electron momentum, right? So this second way of looking at spin-orbit coupling is useful here. This explains why there is a spin-dependent flux that is allowed by the symmetry of graphene. And microscopically, you can even understand it this way. So imagine an electron starting from this side and hop to this second nearest neighbor side. And you can see that along this path, there's an asymmetry on the left and right, right? On the right side, there's an extra atom, while on the left side, there isn't that atom. So there is an electric field pointing perpendicular to this hopping path. And then P cross E give you a Zeeman term which couples to the spin. Right? So that's why if your electron hop from here to here, it has opposite Zeeman field, which is given by P cross E. Right? So this Kane-Mali spin-orbit coupling, it really satisfies all the symmetries of graphene when spin-orbit interaction is included. So then, if it's allowed by symmetry, it probably exists. This term, because it's 2 copies of the Haldane flux, one can see that immediately it will open up a gap at the Dirac point. And this Dirac mass term is opposite for the 2 values, like the case of the Haldane term. But now it's also opposite for the 2 spins. Right? So this is the Kane-Mali mass term. Now, of course, in the carbon system, the spin-orbit interaction is extremely small. So this term, in practice, is vanishingly small. So that quantum spin Hall effect has not been seen in a single layer of graphene so far. But it really illustrates that this topological states with time reversal symmetry. And again, we can look at the domain wall between this Kane-Mali insulating states and the atomic insulator, where we introduce a sublattice potential difference. And now, to understand what happens near the domain wall, near the boundary, we get a spin-full version of the Dirac equation with a mass domain wall, right? So the not only that in one valley there's a mass sign change, but also the mass sign change is opposite for the 2 spin states. So that's why we generalize from 2-component Dirac equation to 4-component Dirac equation. 2 components coming from the sublattice, 2 coming from the spin. Okay, so that's and the net result is that again, solving this domain wall problem, there are now 2 branches of subgap states, and one has spin up, one has spin down, and they move in opposite directions. And the whole system now is time reversal invariant, right? So the time reversal partner of a spin up state moving in one direction is the spin down state moving in the opposite direction. Okay. So to summarize, this gives rise to a protected edge modes at the boundary of the K-Meili insulator, and it differs from a trivial insulator by a Dirac mass reversal. But now we're dealing with four-component Dirac equation in the presence of time-Russell symmetry. And really, this band crossing at the edge is protected by the time-Russell symmetry of spin-1 half particles, and is known as a Kramer degeneracy. So provided time-Russell symmetry is present, these edge states are robust. So I won't go into the details, but again, to understand the topology of these time-Russell invariant insulators, one need to look at the electron wave function in the entire Brillouin zone. Right? So again, the change of topology can be inferred from the mass change of the Dirac equation, but to know which side is trivial, which side is non-trivial, requires knowing the wave function in the whole Brillouin zone. But once again, this parity symmetry helps. So if you have an inversion symmetry, once again, there's a general Z formula for the Z2 index. This holds in all time-Russell invariant systems, irrespective of whether time inversion is present or not. And this general formula involves the Berry curvature. I didn't have time to introduce it in my previous lecture, but you heard it from Feng Wan's talk. The Berry curvature integrate over half of the Brillouin zone, and then subtract the term which is the boundary integral of the Berry connection, mod 2. Now, in this formula, you might think that by Stokes' theorem, this has to vanish, right? The integral of Berry curvature over a region is exactly equal to the Berry phase around the boundary. But this formula is used under the following condition, that we have to choose states at k and minus k according to time reversed condition. The states at k and minus k has to form time reversed pairs. So under this condition, then this quantity put in the bracket is gauge invariant mod 2. Okay, so this quantity mod 2 is a Z2 index. Now, in the presence of the inversion time-Russell symmetry, the bands are doubly degenerate at every momentum k, and that's because now this PT operator is anti-unitary, but it's squared to -1. It's because time-Russell squares to -1 for spin-full electrons. And again, one can now pick this gauge. Just like this morning, we picked a gauge where states are related by the PT symmetry. Here we pick the same gauge. This should be a plus sign. So we choose a gauge where UK at momentum k, we choose the bands into two. We divide the bands into two groups, and one you can think of it as spin-up states, and the other is like spin-down states obtained by acting the PT operator on the spin-up states. Okay. So once you choose this gauge, then just like what we heard this morning, that the integral of Berry curvature along a closed path now becomes equal to pi mod 2 pi. But now there are both spin-up, spin-down species, right? So you get pi plus pi, which is 2 pi. Right? So the integral of Berry curvature along this line m gamma n now becomes 2 pi. Okay, and so the Z2 index becomes 1 if the product of the parity eigenvalue is -1. Right? On the other hand, if the product parity eigenvalue is +1, then the line integral of Berry connection is 0. So once again, what we see is that the Z2 index just becomes the product parity eigenvalue at high symmetry points. Right? So this also explains why in this graphene model, the K-Meili term immediately leads to a 2D TI. Right? So basically the same parity criterion can be used in 3 different contexts. For spinless electrons with time-Russell symmetry, when the product parity eigenvalue is -1, it implies there has to be a Dirac point in half of the Brillouin zone. In systems without time-Russell symmetry, then this Berry phase of pi implies that the Chen number in the entire Brillouin zone has to be an odd integer. So the system has to be a Chen insulator. And now, in systems with time-Russell symmetry and with spin-orbit coupling, the product parity being -1 immediately implies it's a 2D TI. So the same criterion can be used in 3 different contexts to infer the topology or the existence of Dirac point. Okay, so although the K-Malay state is not realized in graphene due to the vanishingly small spin-orbit interaction, it turned out that in a closed variant of the K-Malay state is realized in this transition metal dichalcogenides in monolayer form. So most of the study of the TMDs in monolayer are in the so-called 1H structure. This is a structure with a 3-fold rotation symmetry. This is a view from the top, consisting of the transition metal atom shown in this blue color and the chalcogenide atom shown in the both layer above and both the layer below shown in yellow. So this type of structure are large gap semiconductors. They are not topological, at least not by itself. There's a lot of beautiful optical studies, and Feng probably will talk about it in the next lecture. So here I'm focusing a different structure, the so-called 1T prime structure. So these are structure you can think of it more or less consists of chains. It has a monoclinic structure. And so what our group, we realized that this 1T prime structure actually leads to a 2D topological insulator. This is the first principles calculation. And basically the conduction band comes from the tungsten, the transition metal d orbital, and the valence band coming from the chalcogenide p orbital. And you see that the conduction band d orbital comes down and goes below the Fermi energy, while the p orbital goes above the Fermi energy. So there is this band inversion around the gamma point. And then in the absence of, when we turn off spin-orbit coupling in the calculation, after this band inversion, there are 2 Dirac points along this line, gamma and y, shown in this red dots here. So this is the analog of the Dirac point in graphene. So in graphene, because of the 3-fold symmetry, the Dirac point are located at the corner of the Brillouin zone, K point. But in this structure, the symmetry is much lower, so the Dirac point is not pinned to a special point, but it's pinned to on this high symmetry line. It's a line. There's a glide reflection symmetry around this line. But when we turn on spin-orbit coupling, you see again it opened up a gap at this Dirac point and leading to insulating state. So this is basically very much similar to the K-Malay model. Turning on spin-orbit to the Dirac point generates the 2D TI. And here, the spin-orbit interaction in these materials are actually much larger than graphene because it involves heavy elements like tungsten. And the gap due to spin-orbit is on the order of 100 millielectron volt. And you can see that near the edge, there are these edge states, counter-propagating edge modes with opposite spin polarization. So this is also a good example to sort of connect 2 scenarios of 2, let's say, mechanisms for the generating a TI. So in mercury telluride, those systems, the system is close to band inversion. So we have, let's say, 2 bands, parabolic bands. They touch each other under some changing parameters, and then they open up gap. Right? So in these systems, all the physics happen right near gamma point. Right? While in these systems, what happens that the bands are inverted by a large amount. There's a big inverted gap at gamma. But without spin-orbit coupling, there are these symmetry-protected Dirac points, okay, due to this PT symmetry. And then spin-orbit coupling opens up a small gap so that in this insulating state, the fundamental gap is not at gamma, but at the original Dirac point. Right? So these 2 scenarios, this is more for mercury telluride, this Bernwick, Hughes, Zhang model. And this is more like the K-Malay. And in this material, it's you can think of it's sort of you can smoothly connect the 2 regimes. Okay, So in this material, the fundamental gap in the insulating state is much smaller than the inverted gap at gamma, right? The fundamental gap is at the Dirac point. Yes?
Should the Dirac point be fixed to zero energy somehow?
No,
because
no.
in graphene, it's like filling that controls that the Dirac point is at the zero
So
energy.
in these systems, at charge neutrality, the Fermi energy would be exact at Dirac point because you want equal number of empty and occupied states at charge neutrality.
So it's guaranteed.
Yeah, it's guaranteed. Yeah. So I mean, the energy is not the zero doesn't have a special meaning, but the statement is that the chemical potential would be exact at Dirac point at charge neutrality. The bands are not E minus E symmetric. Put this way. So zero energy doesn't mean, but doesn't have much meaning. But the chemical potential is at the Dirac point. So in these materials, so in this aspect, it's closer to the K-Malin model. On the other hand, these Dirac points are still relatively close to the gamma point in the Brillouin zone. So one can build a full model which is now expanded in the vicinity of gamma point, right? So you see, if you take this model, I'll show you anyway. So there's a parabolic bands for the d orbital. There's a parabolic bands for the p orbital, and then there is this term v1, which is without spin orbit coupling. And with these diagonal terms and the V1 term, it generates a Dirac points, right? Very much like in graphene. But then the V2 term is the spin orbit term, and that generates mass at the two Dirac points with opposite sign. So that is the K-Malin type of mass. So the important thing that here, in total, we're just using 4 degrees of freedom: the d orbital, the p orbital, and the spin degrees of freedom, right? But this model, it effectively gives you 2 values, right? When you solve this spectrum, it naturally gives you 2 values, and this V2 term, right, which is a spin orbit term, right? When you write in the vicinity of these Dirac points, it generates mass that are opposite sign for the 2 values and opposite for the spins. I give you the K-Malin mass. So in other words, for these 2 different scenarios, one can understand the connection between them, in this way. Okay, so right, so back then, when we look at this family of 1T prime monolayer materials, and this is tungsten diselenide. There's one material for which the 1T prime structure is naturally the ground state, and this is tungsten ditelluride. But when we did the calculation, it turned out that there's a large band inversion at the gamma point, but the fundamental gap in the presence of spin orbit interaction is actually negative. So we worried a lot that whether this tungsten ditelluride could be a good choice. We thought of various ways to give you to do something like strain to give you a large fundamental gap. But experimentalists got interested anyway, and it turned out nature seems to be more kind. So this is a work by Sanfeng Wu, starting us when he was a graduate student at Washington, Seattle, and then later a postdoc at MIT. And you see that they chose this tungsten ditelluride, and in monolayer form, you see that as a different gate voltage, and he will talk about it in the afternoon. So all I want to say that here you see the nice quantization. That these helical edge states give you conductance, E squared over H. And when you apply magnetic field, the time rule symmetry is broken, so the edge states become insulating. It's all consistent with the 2D TI. Okay, so any questions so far? Okay, so now let me then move on to quantum geometry in 2D materials. So I'm going to briefly discuss barrier curvature and anomalous velocity that you heard already from Feng Wang's talk. Not only does this give rise to anomalous Hall effect, to a quantum anomalous Hall effect, but also I want to briefly mention recent works on the nonlinear Hall effect due to the barrier curvature. So, so if you look at the semi-classical equation of motion for a wave packet, electron moving in a crystal, the velocity not only is given by the derivative of energy with respect to k, but there's an additional contribution to the velocity that is related to this barrier curvature. and this is a cross product between the barrier curvature and the time derivative of momentum. So, so turn out this anomalous velocity underlies all these interesting phenomena of the anomalous Hall effect, of the quantum anomalous Hall effect. So one way to think of this is the following: that we know that the electron wave function has an envelope part and has a part which is within each unit cell, right? So this first piece, the group velocity, only describes the center of mass motion of a wave packet that is related to the envelope function. But as an electron moves under an electric field, the wave function within each unit cell is also changing. So in particular, it could be that as k moves as the momentum changes from k to k plus dk, the wave function within the unit cell also redistributes itself. Okay, so for example, in the honeycomb lattice in the graphene, right, there are two sublattices, the A and B sublattice. So at one wave vector k, the electron may be more centered on the A sublattice. But at a different value of k momentum, the wave function may be more centered on the B sublattice. So as momentum changes from k to k plus dk, the wave function redistributes from A sublattice to the B sublattice. So this generates another velocity. Right? This is known as the anomalous velocity. Okay, so so it's really some kind of a, you can think of there's an intra-unit cell current flow. Right? A current flow not coming from the center of mass motion, but coming from the electron density within the unit cell. So so once we take the integral of the anomalous velocity over all the occupied states, we get a transverse current, right? Because this anomalous velocity is always perpendicular to the applied electric field. So this leads to a transverse current. Now, at the level of linear response, we see that we are looking for a transverse current that's linearly proportional to applied electric field. So then, in order to get the linear response Hall current, in this expression, we would substitute F with F naught, which is the equilibrium distribution, right? And this immediately gives us the expression for Hall conductivity. So it's an integral of barrier curvature multiplied by the equilibrium Fermi Dirac distribution over the K space. Okay, and for the case of an insulator, the Fermi distribution is 1 for the occupied states. So this formula becomes the integral barrier curvature over the entire Brillouin zone for all occupied states. And this quantity is quantized into an integer multiple of E squared of H. In the case of a metal, then we are taking the integral over all the occupied states. The band is partially full, right? So this becomes integral over states below the Fermi surface. Now, in systems with time reversal invariance, then it is guaranteed that the energy at k and minus k are equal. So they have the same equilibrium distribution. Also, it guarantees that the barrier curvature at k and minus k are opposite. So then when we look at this Hall conductivity, it has to be 0. Right? That's why a time reversal invariant system does not have Hall conductivity at level of linear response. Now, what's interesting is that, as you heard from this morning from Feng Wang, in many of these 2D materials, right, they are time reversal invariant, but they break inversion symmetry. So in this case, the barrier curvature can still be allowed, can be finite in K space, but K and minus K has to have opposite barrier curvature, right? So, so these barrier curvature concentrated, for example, near the corner of the Brillouin zone in bilayer graphene, in transition metal dichalcogenides. The barrier curvature is very large in the vicinity of the K point, and it's equivalent to hundreds of Tesla magnetic field, right? But as Feng said this morning, that overall the system, because there's a K and minus K states being equally occupied, the effect of such large barrier curvature is not revealed. So we have been thinking, is there a way to reveal the effect of this large barrier curvature in time reversal invariant but inversion breaking materials? So now when we look at the expression for the anomalous current, if we go now beyond the linear response theory, right? So when we apply electric field to a metal, the Fermi surface is not the equilibrium Fermi surface. It will be displaced in k-space, right? So in the current carrying state, the distribution deviates from equilibrium distribution, and the change of the distribution function is also an odd function of k. Right? There are more electrons moving to the right than those moving to the left. So then, if we look at the transverse current to second order in applied electric field, then this integrand is a product of two odd functions of k, so it's finite. So this means that at the second order response, there could be a transverse current. Right? So once you have to realize this scenario, what we need is we want electrons that are moving forward to have barrier curvature which is plus, let's say, while electron moving backwards has opposite barrier curvature. So in such a system, then this can be realized. So this is something that work with Inti Soderman, a former postdoc at MIT. So, so indeed, when we look at this second order response, we find that, it leads to two effects. This barrier curvature leads to two effects within this, this transport theory framework. So when we apply electric field that oscillates at frequency omega to second order response, there's a DC current. This is known as the photocurrent effect. There's also an oscillating current at a frequency 2 omega. So basically, when we have a second order response, there's either omega plus omega, that is a 2 omega response, and omega minus omega, which is a DC response. And it turns out both effects in this low frequency limit, when the transport theory applies, they are described by the same coefficient, which is a rank 3 tensor, chi ABC. And this chi is given by the barrier curvature integrated over the derivative of the equilibrium distribution with respect to k, right? Because we are dealing with a second order response. So what enters here is a change of the distribution due to the electric field. And this can be rewritten by integration by part. It becomes a derivative of barrier curvature with respect to k integrated over all occupied states. Okay, so this quantity, we call it a barrier curvature dipole because this omega is barrier curvature, but now we're dealing with the derivative of barrier curvature with respect to k. This quantity, it has a symmetry of a dipole moment of barrier curvature. So this expression tells us that the response involves the barrier curvature dipole, and the prefactor is essentially the same as the Joule form. This form 1 plus I omega tau in the denominator. So if we go to the limit omega tau is much bigger than 1, then the photocurrent becomes a universal formula. It's independent of tau. It only depends on the barrier curvature dipole. So in other words, there is a dissipationless photocurrent purely coming from barrier curvature dipole of the Fermi surface. And this is the analog of the anomalous Hall effect level of linear response. And this has been first pointed out by these two papers that circularly polarized light can generate a DC current due to these barrier curvature effects. So we also look at the second harmonic generation. We formulated everything in terms of barrier curvature dipole and look at the second order response at 2 omega. Okay, and in this 2 omega limit, then this is also related to the barrier curvature dipole. And in the low frequency limit, the scattering rate tau enters. Nonetheless, in terms of symmetry, it's all determined by the barrier curvature dipole. Now, usually the SHG, second harmonic generation, is discussed widely in the optical community when the photon energy is in the visible range. And here you shine light of one color, and you get light of a different color. Right? The frequency doubles. What we realized in this calculation then is that even at very low frequency regime, a few hertz or kilohertz, there is an electrical second harmonic generation that passing current at frequency omega can generate a transverse voltage at a frequency 2 omega. And this gives a way of revealing this barrier curvature dipole in the system. So, right, so if I look at 2D materials, to get this barrier curvature dipole, the system is required to have a preferred in-plane axis. So the material has to have a polar axis within the plane, and then applying electric field transverse to the polar axis will give you both a DC current and 2 omega current parallel to the polar axis. Now, one of the ways to generate this barrier curvature dipole is, again, we take a Dirac model, take the case of a Dirac fermion. We know that once Dirac fermion opened up a gap, there's a barrier curvature. But in the simplest Dirac equation, it's rotationally invariant. So there's barrier curvature, but no barrier curvature dipole. So we realized that once we give the Dirac fermion a tilt, right? So instead of a dispersion like this, if we take a Dirac fermion that is like this, I don't know if it's, take a case of a tilted Dirac fermion, right? And then open up a gap. And this would give you a barrier curvature dipole. So we played with several materials. I'll skip the details. And but in the end, it turned out that what experimentalists found is again this tungsten diterite. Right? Yes, question?
So, yeah, the amount of tilt is important here?
It's important, yeah.
So how, if you go to the type 2 Dirac, how will it change?
Right. I mean, for type 2 Dirac point, it depends on also the whole Fermi surface.
Yeah,
right? Yeah. So then I cannot make a general statement there. But if you take a tilted Dirac fermion, it doesn't have to be tilted way over. This already gives you a barrier curvature dipole. So I've described the monolayer tungsten diterite is a 2D TI. You take two layers together, it's not topological anymore. Because 2D TI has a Z2 index. 2 layers is equivalent to topological trivial. However, it turned out to have a very large barrier curvature dipole, as I'll describe. And so this is experiments that they run current at a frequency omega and detect the signal in the transverse direction, transverse voltage at 2 omega. And this is the voltage plotted as a function of the instant current. And you see that in the transverse direction, there's a large 2 omega voltage that's proportional to current squared. So this is the first detection of a nonlinear Hall effect in a completely time-reversal invariant non-magnetic system and without any external magnetic field. Okay, so here what happens is that the monolayer WTE2 is actually inversion symmetric, but when you stack 2 layers together, the stacking itself breaks inversion symmetry. And one way to think of it is that each layer of the WTE2 give you a Dirac cone, right? So the K-Meili spin-orbit interaction opens up a gap, but that gap is quite small. So for this purpose, we can neglect it. When you put 2 layers together, the Dirac cones hybridize with each other, they get split. And this splitting of the Dirac cone generates the barrier curvature, but also the 2 Dirac cones are offset in K-space, and that gives you a barrier curvature dipole. So this is, roughly speaking, how we get this barrier curvature dipole in the system. Again, we compared it with the DFT calculation of the barrier curvature dipole, and experimentally you can change the band structure by applying a displacement field, right? And the barrier curvature dipole changes with displacement field, and experimentally the measured second harmonic voltage also varies with the applied field. So the experiments and theory are qualitatively agreement with each other. So basically, to summarize, this part of there's nowadays a lot of interest in nonlinear response in semi-metals, topological materials, and the optical community has been mostly focusing on things like SSG, etc., in the visible range, in the infrared range, and these effects usually come from interband transition, right? For example, when you excite electrons from the valence band to the conduction band, it leads to a photocurrent, well, what I've been talking about is purely coming from the Fermi surface, right? So we're using the Boltzmann equation to describe the physics associated with anomalous velocity. So these are all at very low frequency. For example, this experiment is done at only 100 hertz, right? I think in the end, it'll be very interesting to sort of go to this intermediate range of the terahertz range, where there's a lot of interesting potential applications. And I think as long as interband transition is not involved, this type of barrier curvature mechanism can describe this nonlinear response. And there's a lot more to be explored. Okay, so to summarize, been so far discussing topology and quantum geometry in 2D materials, I hope I've sort of convinced you that there's in some sense a magic bullet, that there's the simplest ingredient for all these phenomena, topological states and quantum geometry is basically Dirac point. Right? Starting from Dirac point, we can think of various ways of opening up the gap, generate Dirac mass. It leads to topologically distinct insulating states. And on the boundary between these states, there are gapless edge states. Even a zero gap Dirac point, when you apply magnetic field, it generates this quantum Hall effect. There's a very interesting zero energy lambda level that gives you these ambipolar edge modes and leads to interesting thermoelectric effects. And also in the bulk of a Dirac material, there's barrier curvature that generates both the anomalous Hall effect and the nonlinear Hall effect. Right? So it's, in some sense, this Dirac point unifies right, all these different phenomena of topology and quantum geometry. Okay, so now let me move on to something else. Okay. Is there any questions? Yes?
How does temperature influence the transport properties which are due to the barrier curvature dipole?
That's a great question, yeah. So in this experiment, so there is a temperature-dependent measurement here. I think above 100 Kelvin or so, the signal get much more reduced. And that's consistent with the small gap, in this WT2 bilayer system. Yes.
Experimentally, did the frequency dependence get measured?
Right, that also get measured. Now in transport regime, the frequency went all the way to like maybe a few kilohertz, and it roughly stays constant. And that is all consistent with the fact that omega is still much smaller than 1/tau.
So what
scattering rate.
The frequency go to say megahertz or even to gigahertz?
Yeah, then actually according to this formula, it should decrease. Right. So the frequency dependence is basically just like the Jude peak. Right. This behavior is the same as in Jude theory, Jude peak.
Yeah, but usually the tau should be in terahertz range, right? So
Yeah.
that means even in megahertz or gigahertz, it should still remain at
That's
the
right.
constant.
That's right. Yeah.
So
Correct.
experimentally, was it?
They only measure up to kilohertz. Yeah. So it could go to higher frequency, but just
what's
as
the
it,
experimental limitation of why can't it go to say megahertz?
I think they just didn't try. Yeah. But yeah, they should be trying. Yeah. And I agree with you that for this material, this 1/tau is at least in the terahertz range, or maybe even higher, right? Because
the measurement is just locking was not in the gigahertz generator, which is not applied on the higher frequency.
Some locking can go to at least tens or hundreds of megahertz.
yeah, it's worth trying, definitely.
Question.
Yes.
I think the semi-classical equation is true only perturbatively. So can you still use that when you go to the second order response?
Right. Yeah, that's a good question. So what we recently are doing is we are trying to do the full quantum mechanical calculation perturbatively in the applied electric field. The usual linear response theory stops at first order, but nothing prevents you from going to the second order. In fact, there are people in the theoretical literature studying SHG using this, looking at how the density matrix changes to second order in electric field. And so far, what we find is that all these terms survive. Yeah. So although I've derived it using the transport equation, the full quantum mechanical calculation gives the same result. Yeah. So in this intraband limit.
Also, like in the anomalous Hove signal, people talk about sometimes defect can
Exactly.
be complicated, like
Exactly,
side jump
exactly.
and so on
Right.
and so forth.
Right,
Will
right,
they
right.
contribute to this?
Absolutely, yeah. So, right, it's an excellent question. So, right, so what the Feng is saying that in the case of an anomalous Hall effect, there is a spiral curvature contribution that's called the intrinsic contribution, but there are also effects coming from the disorder scattering, things like skew scattering, etc. So, so here we have assumed that the disorder is completely featureless, so it's all captured by a single relaxation rate tau. So in reality, disorder can have more subtle effects. So in the follow-up work, I didn't have a reference here. So we studied a case where disorder scattering generates this second-order response. So that imaging systems, which like the TMD, which has 3-4 rotation symmetry, there the barrier curvature is present, but barrier curvature dipole is forbidden. Right? But we show that due to disorder scattering, it actually also generates SHG. But it have a different frequency dependence than the one I'm talking about here. Yeah, so it's a good question. Okay, so so now let me move on to the next part. Okay, so the so much time do I have?
Half hour?
Okay.
20 minutes?
Right. So so the rest of these today's lecture and tomorrow's lecture is more so not on a different subject. It's more about correlated electron systems. So so it's very different. These are very different from the sand metals and the insulators we talk about here. And one big difference is that the sort of the underlying electronic structure has a big Fermi surface, right? Instead of having a single Dirac point or a few Dirac points. So for example, in the cuprates, there's a Fermi surface, and a large part of the phase diagram, it seems something happening to the Fermi surface. So whatever it is, right, it seems very different. Certainly very, very different from the case of a Dirac point. And of course, that all these recent activities on these correlated electron physics in moiré materials has really, in some sense, given a new life to these correlated electron systems. And we see all kinds of interesting phenomena that you heard this morning from Feng, correlated insulating states, superconductivity. They can be tuned by pressure, by electric field, by twist angle, and the amazing phenomena seems to be going on and on. Right? That also ferromagnetism, Chen insulator, and et cetera, et cetera. So, so again, there are many different ways to look at these systems, and one scenario involves a flat band. For example, in twisted barrier graphene, when you go to this magic angle, the first found by Alan McDonald, you see the bandwidths become very small. Right? You can have an almost flat band. And Feng talked about this tri-layer graphene on HBN. There's also studies on twisted TMD, where you have also isolated flat bands. On the other hand, I want to also mention that that this general idea that you take a moiré pattern and that can do interesting things to the electronic structure seems to be a recurring theme, right? And this work is as little known as this twisted barrier graphene is widely known, right? So probably nobody paid any attention to this. So in this one, these are basically people doing growing films of lead telluride and films of tin telluride, etc. Because these different materials has different lattice constants, slightly different lattice constants, at the interface between two different materials, the system self-organized into an array of dislocations. Basically, dislocation is a way to match for the system to relax the strain and match the lattice constant as much as they can. And what end up happens is that at the interface, there's a periodic array of these dislocations. And the period, the superlattice period is again on the order of 10 nanometers. Okay. Now, what's interesting is that none of these underlying materials are superconducting. These are all semiconductors. But the interface becomes superconducting with a TC on the order of a few Kelvin, right? Kelvin. So a few years ago, we got interested because some of these materials are topological insulators. topological crystalline insulators. So they also have Dirac fermions. And so we play with a simplest model. We think of this Dirac fermion moving in the presence of a periodic string. And what happens is that we get the Dirac point remains, but now the Dirac velocity vanishes. Right? As the electron moves, through this periodic gauge field, the Dirac velocity can be greatly suppressed. So we get what we call a partially flat band. Right? So in this particular model, in the vicinity of the Dirac point, we have something like a flat band, but it's not separate from higher bands. Right? So this we call a partially flat band. So the question that I'm going to address is like, is there all these different systems where we have a moiré superlattice, right? There are many different perspectives you can take, right, on what is causing the correlation phenomenon. So one approach is to take the flat band limit, very much like quantum Hall physics. If we have a complete flat band, then you have a very strong divergence of denser states, and that leads to interesting correlated states of matter. But the approach I'm taking is, again, sort of coming from my background in this problem, that the bands may not necessarily be completely flat, but maybe the bands are flat only in part of the momentum space. So we get high density states near the Fermi energy. Right? So, so this is, there's one example of this is the by Hove singularity. Right? So that if you have a by Hove singularity in 2 dimensions, the density state has a logarithmic divergence. Right? The full bandwidth may not be that small, but you get a log divergence at the particular energy. So I'm going to describe another version of the Hove singularity, what we call high order Hove singularity, where the density state has a stronger divergence, a power law divergence. So we're going to look into basically, this is very sort of in my own very idiosyncratic point of view, let's say, that even in systems where the band is not completely flat, one can get correlation phenomena from these high density state around the Fermi energy. So the motivation is actually coming from this early STM experiment on twisted pattern graphene almost 10 years ago from Radicus group. And these are twisted pattern graphene with different twist angles. And you see that the DIDV spectrum shows that there are very pronounced peaks. Right? So these are by Hove singularities in the moiré band. Okay? And in this twist angle, there's by Hove singularity in the conduction band, in the valence band. The energy separation between them is about a few tens of millielectron volt. This gives a rough idea of the bandwidth. But when you go to much smaller twist angle, around 1.1 degrees, you can see that the 2 by Hove peaks are much closer in energy. So this is all consistent with as you move close to the magic angle, the bandwidth get reduced. One of the great things about having the moiré band, right, is that one can tune the carrier density. So one can change the carrier within a band, change the filling from the bottom of the band almost to complete filling up to the top of the band, right? And this is the measurement of twisted pattern graphene under pressure. And you see that as you start to fill a band, the Hall connectivity changes sign, right? This sign change is again within a band. Is telling us that there is a transition from electron type of carrier to Hall type of carrier. This is a characteristic feature of this by Hove singularity. And so now let me go back to this by Hove singularity and what exactly it is. So this really comes from the saddle point of the energy dispersion, and this presence of by Hove singularity is actually mathematically guaranteed. It occurs generically in every band with a smooth band structure. It's guaranteed by basically the topology of periodic functions. So we know that the momentum k has to live in a Brillouin zone, which is topologically a torus. Right? So if we plot energy as a function of k, so here energy is the vertical axis. Right? So at every energy, we can draw constant energy contours in the Brillouin zone, which is represented by this torus. And as you can see, that as you start from the bottom of the band, you get the Fermi contours which are contractible to a point. Near the top of the band, you get contours which are also contractible to a point. But somewhere in between, right, because of the topology of the torus, you have to, the constant energy contour changes from a contractible loop to two non-contractible loops. Right? And right at this bifurcation point, this is a saddle point. Right? The dispersion changes from electron-like to hole-like. So this Van Hove singularity is completely generic. They exist in every band, guaranteed by the topology of periodic functions over the torus. Okay? So we're not talking about topology of the wave function anymore. We're just talking about the topology of energy dispersion. Okay? E as a function of k. So mathematically, the saddle point is defined like this. This saddle point is defined as where the velocity vanishes, and then we have to expand this energy in the vicinity of the saddle point to second order in k, and there is a quadratic form, and the determinant of that quadratic form, when it's positive, it describes a band extrema, band minimum or band maxima, but if the determinant of that quadratic form is negative, it describes the saddle points. A simple example is this, kx squared minus ky squared, and you can see the constant energy contour. The Fermi contour reconnects, right? It changes from bending this way to bending the opposite way, and right at this Van Hove energy, the Fermi contour, they intersect each other in a straight line. So this leads to a logarithmic divergence of density of state in 2 dimensions. So there's a long history of thinking about this correlation effects when the Fermi energy is close to this divergent density of state. It basically leads to various kinds of possible instabilities, right? Because in a simple sort of a mean field theory, the susceptibility is proportional to the non-interaction susceptibility enhanced by this Stoner factor. But when the bare susceptibility diverges as density of state, all these susceptibilities like ferromagnetism, superconductivity, pneumaticity, density wave, they all diverge, right? They all have logarithmic divergence. So, this naturally leads to competing instabilities. So this scenario has been studied quite a lot in different contexts, in the context of cuprates, rusinates, monolayer graphene, etc. Now, the way we think of it is that the 2D materials provide a new and ideal platform for studying this whole physics. First, one can always use gating to bring the Fermi energy of chemical potential to this Van Hove filling without introducing disorder. Right? That's one advantage. Moreover, these 2D materials, as you heard from Feng, that they are also tunable by electric fields, by strain, by twist angle. So not only we can put Fermi energy to the Van Hove singularity, but also we can design, we can maybe tune the energy dispersion in the vicinity of this Van Hove point. Right? So this leads to an additional tuning parameter. So the question is now, what would be the phase diagram like as a function of doping, as a function of tuning parameters, as a function of temperature. Right? So we know that in the high temperature region, we change from electron to whole Fermi liquid when the Fermi energy crosses this Van Hove energy. But what happens at low temperature? So, so when I look at this, this Fermi surface of twisted barrier graphene, not only it has this Van Hove singularity, but interestingly, this Van Hove singularity changes dramatically as a function of twist angle. So this is the Fermi surface plot at 1.8 degree, and you see that there's Van Hove singularity along the high symmetry line, gamma m direction, right? There are 3 Van Hove singularity coming from the k value. There's also Van Hove singularity coming from the minus k value. They're the time reverse partner. So from now on, I'm only going to draw bands in one value. Now, but when you go to the 1.05 degree, now there are actually 6 Van Hove singularities, and they are away from the high symmetry line. So we know that this Van Hove singularity are guaranteed. They're topologically stable objects. Right? They can move around, But how can they change from the number of the Van Hove singularity change from 3 to 6? Right? So what happened that there is in a sense, a topological transition. So this means that there must be a critical twist angle where each Van Hove point, saddle points, splits into 2. And to understand this transition of the saddle points, one can just look at the dispersion around these this original saddle points. Usually, when we expand the energy to quadratic level, we get px squared and py squared. But here, let me go to high orders. So there's a third order term and the fourth order term, and et cetera, right? One can keep going. But it turned out we can stop at this level. So when the beta, one of the quadratic coefficients is positive, we get a saddle points. This is a canonical saddle points leading to logarithmic diverging densive states. When the coefficient beta changes to negative, now we get a energy extrema at p equals 0. But because of the presence of these higher order terms, 2 new saddle points appear, right, away from p equals 0. So, and the constant energy contour is shown like this. Right? We get basically 2 new saddle points. Right at the transition, when beta is 0, what we see is that the 2 Fermi contours touch each other tangentially. Right? And this is something new. Right? This is something new. This is what we call a high order Van Hove singularity, because it relies on including high order terms in the expansion. Okay. And so as we change the twist angle, these coefficients in the expansion varies smoothly. So at larger twist angle, we have the situation shown on the left, and at larger twist angle, like 1.8 degree, we have the situation shown on the left. At small twist angle, like around 1 degree, we have the situation shown on the right. So somewhere in the middle, just by continuity, there has to be a special angle where the quadratic coefficient, one of them vanishes. And indeed, when we look at the band structure calculations, at certain twist angles, we see that at the Van Hove singularity, the bands, the Fermi surface touch each other quadratically. Right? This is all consistent with what we expect from this expansion. So this is what we're going to focus on, this high order saddle points. So in this high order saddle points, the energy dispersion has this scaling property. The x and y direction now scale differently with each other. And we get Fermi contours that touch each other tangentially. I want to emphasize that this situation occurs only requiring tuning a single parameter. Right? So when we tune the parameters, all we need is to change the sign of one of the quadratic coefficients from positive to negative. And right at the transition point, we are left with this high order saddle points. So generally, changing one parameter, such as twist angle or electric field, is sufficient to give us this high order saddle points. Now, when we look at these denser states, now it has actually a much stronger divergence. Instead of logarithmic, it's actually power law divergence with an exponent, which is minus a quarter. Also, this denser state is asymmetric. At positive energy and negative energy, they differ by a factor of the square root of 2. Okay, so all coming from just this dispersion. And so this is something that's different from the ordinary Van Hove singularity. So it's too much to keep saying high order Van Hove singularity. So we introduce a phrase, a terminology that we call it supermetal. Right? These are, let me explain what I mean. So we know that metals have a finite Fermi surface, finite denser states. Semi-metal, like a Dirac semi-metal, has a vanishing denser state. It's in between a metal and an insulator. While here, we have a situation where it has infinite denser state. So, in that sense, it can be called a supermetal. Also, another way to think about it is that metals have finite charge susceptibility and spin susceptibility, right? But if you have a divergent dense state, it also means that the charge compressibility is infinite and the spin susceptibility is infinite. In that sense, this is a super compressible. It's also super paramagnetic. So that's why I call it supermetal. Anyway, so leaving names aside. Moreover, one can look at the dense state both at this higher Van singularity, or if you perturb it away. So this beta term drive the system from high order Van singularity to ordinary Van singularity, and Noah, who is here, was able to actually find the full expression for the dense state, both at and away from this high order condition, and the final result in terms of this elliptic integrals. So we're going to use this formula to look at the experiments. So, the intrinsic value graphene, the STM experiments, is a direct way of measuring the dense state, and there's been 3 groups, including people here, Ali Hassani's group. And in general, the qualitative features are similar. That if you look at the various twist angles, there's always a Van Hove singularity, right? And as you go to smaller twist angles, these Van Hove singularities start to become closer in energy. They're showing us the general reduction of the bandwidth. So this is the DIDV spectrum right at the magic angle, 1.1 degrees. Well, if we look at these data, we plot the DIDV and as function of energy in the log-log plot. So if it's a power law dense state, then in this log-log plot, we should see straight lines. And indeed, you see that these data points fall in a straight line. This red dots has a slope of -1/4. Moreover, because of this high order Van Hove singularity has an intrinsic asymmetry at +e and -e, they differ by a square root of 2. So it means that these 2 straight lines should be offset by a square root of 2. Okay, and here what we get is close. Right. So this is evidence that at least in this particular device, the system is close to this high order Van Hove singularity.
But in the magic angle, shouldn't correlation be very strong, and you are not probing single?
So we are looking at the Charlton-Charlie point. The Fermi energy is right in the middle. Yeah. So when you move the Fermi energy, I'll show the data actually. Yeah. So the rounding is, one could be the instrumentation, and the second it could be due to disorder. Okay. So there's rounding, and also.
Do you think this is near the angle where the high order, the supermetal would be?
Yeah, exactly. Yeah. This is at least in this device.
Yeah.
So this is thanks to all this fitting comes from Noah. Took the data from the Columbia group and. Now we can also look at different twist angles, and now you can also fit all these different twist angle data using the dense state that is shown here, right? And from this fitting, you can extract basically all the parameters in this energy dispersion, and basically there's one parameter W, which tells us how far this system is away from the high order Van Hove singularity. It's an energy scale. Basically, it tells us that even when the beta is not 0, if you look at the full expression, right, when beta is 0, we have exactly that high order Van Hove singularity. When beta is small, what happens that in the large energy range, the system can be approximated as high order Van Hove singularity, but it breaks down when energy is smaller than a critical value. There's a cutoff energy scale, a lower energy cutoff, and this W essentially is a lower energy cutoff. And indeed, you see that as you go to this magic angle, this lower energy cutoff become very, very small. So over a wide energy window, the system can be regarded as a high order Van Hove singularity. While if you go to like 2 degrees, the system is far from high order Van Hove. Right. So now I'm almost done. Let me just for today's lecture. But let me just show a few experimental. So far everything I've talked about is basically at the level of single particle physics. Right? The dispersion around the Van Hove singularity, and when Van Hove becomes higher order Van Hove, the dense state has a stronger divergence. What happens if you put the Fermi energy to this Van Hove peak? Right? So this is experimental data now. So the data previously I showed you is when the Fermi energy is right at charge neutrality, and as you gate the device, the Van Hove singularity moves towards Fermi energy, and as you can see from here, as the Van Hove singularity moves to Fermi energy, this peak, single peak splits into two. Right? And this shows up also in the Caltech data, as well as the Princeton data, that Van Hove singularity, when it moves Fermi energy, is split into two peaks. So this is experimental evidence that this Van Hove singularity at Fermi energy that leads to correlation effects. Okay, so in general, right, there are two sort of scenarios one can imagine when Fermi energy is close to the Van Hove singularity. In one scenario is that because of the large density of state, interaction will split these Van Hove peaks. For example, the system can be spin polarized, can be valley polarized, etc. So it's very much like flat band. Right? If you have a high density of state, something interesting happens. But now there's another scenario which doesn't occur in the case of a flat band, and this has to do with the screening. Right? So if you have only a high density of state near Fermi energy, but if the bandwidth itself is still finite, there is a possibility that the screening takes place. Right? So electrons try to move around and stay away from each other. And the screening strength is also related to density of state. Right? The larger the density of state is, the stronger the screening effect is. So screening may restore the system back to a Fermi liquid. So there are these two competing tendencies. This needs to be studied more. So next lecture I'm going to discuss a little bit of that. So if I have 1 minute left, I can very briefly mention that this high order Van Hove singularity, as I said, only requires a tuning one parameter, and so it could be quite generic. In particular, this is another example. Some years ago, we were playing a toy model, right? Like the Hove model is a model on the honeycomb lattice where you have imaginary hopping. So we played with a model on the triangle lattice with imaginary hopping, right? So and turn out for this simple model of triangle lattice with imaginary hopping between nearest neighbors arranged in this way, that you get plus I when you hop along the direction of the arrow and minus I if you're hopping against the direction of the arrows. You get a very interesting scenario that the Fermi surface is shown here. You have 3 pieces of Fermi surface that touch at a single point. So back then we noted that this density of state in this scenario would diverge as a power law. So this is another case of a high order Van Hove singularity. If you look at the dispersion in the vicinity of this point, it's a third order polynomial of K. So when the trilayer graphene experiment came out, so we look at the band structure of trilayer graphene using the continuum model in Feng Wang's paper. And this is a calculation from NOAA. Remember that, as Feng said, in this system, you can tune the band structure by the electric field. So these are the 3 different Fermi surface plots at a different electric field. And you see that there are 3 Fermi surfaces that are quite close touch to each other. So at this critical electric field, they are all touched at a single point. So this, again, leads to this the situation of this high order Van Hove singularity. So if you look at dispersion around this gamma point or K point, essentially symmetry only allows 2 terms to third order. One is a K squared term, it's completely isotropic, and the other is this term, this K to the Kx plus Ky to the third power. Right? So when you tune the electric field, the coefficient of the K squared term can be made to vanish. And then you're left with this high order Van Hove singularity with a power law divergent density state. So one thing that immediately follows from this is that because this is a scaling, energy is a scaling function K, it leads to all kinds of scaling relations that may connect to Feng Wang's result, how the density and temperature scales with each other in the resistivity plot. Okay, I'll stop here. Thanks.
We have a few minutes for questions.
How do you expect susceptibilities to behave around these high-order singularities? Is it going to be very similar to normal Van Hove singularities, or will there be anything different?
It's only going to be different, right? Even in the case of the non-interacting susceptibility. for ordinary van Hove, it has a logarithmic divergence as a function of, for example, temperature. But here it has a power law divergence. So it's certainly very different. Yeah.
Could you tell something about the stability of the lattice? Basically, if I couple this fermions with divergent density of states to phonons, will the lattice still be stable, or could there be a lattice instability induced?
Yeah. So absolutely. So this is all related to this question about the this competing instabilities. Right. So so one way to think, you can couple the lattice directly to the phonons. I guess you have in mind, I don't know if you have in mind acoustic phonon or optical phonon. But for example, if you think about the electron coupled to optical phonon, which has a gap, right? You can always imagine integrate all the phonons, and you are left with some electron-electron interaction. So this reduces then, your question then becomes basically, once you include interactions, what happens to these?
But if I could have acoustic phonon, then I can have just the speed of sound
Right.
become a negative, and then the lattice is unstable, right? So that's it.
For acoustic phonon, I need to think about it. Yeah, it's a good question. I need to think about it, right? And in the next lecture, I'm going to describe it. In certain cases, at least, we have a good idea what happens to electrons at high order van Hove singularity in the presence of interactions.
If that's it, then let's thank the speaker again.